Thank you very much, Yahia. Well, first of all, it's a real pleasure to be here. It was also a real privilege to hear it was sold out. That did my credibility as a father no end of good when my daughter held that her dad had sold out a gig in town. It's just so good to be here. I always find it a real pleasure talking to members of the general public. I used to do a lot of talks for the senior learners group at the university, and I can assure you members of the general public are much, much better audiences than your typical undergraduate class who sit there staring into space in complete silence. I've always found these talks to have the most warm, welcoming and interested audience, and I look forward to talking to you over the course of the next 40 minutes or so. So what I'm going to talk about today is the results of one major project I've been involved in, which I should say Yahia has played a huge part on. So I'm really pleased that Yahia could introduce me today. And that's a project called the Environmental Virtual Observatories Project, looking at how cloud computing can support the needs of modern day environmental science. Just before I start though, a little bit of an aside. I hear you're a very bright audience, a very well-read audience. So let's just put that to test. Some of my intellectual heroes, this is a bit of a sub-theme that will pop up throughout the lecture. Can you recognize any of them? Any thoughts? No? Yes. This handsome-looking chap here is Bertrand Russell. Any more? Who's the guy on the right? Strong Lake District connections? Ruskin, absolutely. What about this guy? A bit closer to home for me as a computer scientist. If there's any linguists in the audience? Chomsky. And here? Anybody interested in ecology? Anybody interested in Buddhism? No. Joanna Macy. What do they all have in common? Think about modern academics like myself and think about the kind of figures you see in the screen. What do they all have in common? Yeah. They're all polymaths. They're all really eclectic people. They're hard to pin down. What was Bertrand Russell? He was a mathematician, a logician, a philosopher, a political thinker. What was Ruskin? He was a painter, a geologist, an architect, a commentator on Victorian era. Each of these figures on the screen was a polymath. They embraced multiple subjects. In fact, their intellect was fed by the fact that they were familiar with many different perspectives on the world. Compare that to education of today, when we're trained to be specialists. We're trained in a discipline, in a sub-discipline. In universities, we form departments, we form research groups, we put up big walls around our research groups, we become silos. I think that's completely wrong. I think that's detrimental to education. And if you hold that thought in your minds, I'll come back to that, because that's absolutely a core reason for what we're trying to do and the project at Unfold. It'll take a little bit of time to get back to that, but we shall return to that core topic. Just a little bit about myself and my journey. In some ways, I was a classic professor of computer science for a number of years. I'm a professor of distributed systems, which means I worry about how you program computers when there's more than one. If any of you have done any computer programming, you'll realize that this is a horrendous task, a complex task, not easy by any means. Then think how you program computers when there's 10 of these coordinating to provide a given service, or 100 of these, or 10,000 of these, and the computation spans all these elements and has to run on perhaps 10,000 computers. That becomes very complex, extremely complex. And one of the things I worked on for many years was to try and raise the abstraction so you could program these things in an effective way and manage this sheer complexity. But a few years ago, I started to change in my interests. I started to want to engage more with real-world problems. So I've moved from sort of fundamental research in computer science to much more applied work. And I've actually found that very rewarding, working on real-world problems. I'll come back to that as well, because it's very rewarding, rather than locked in a lab thinking about how you program complex computer systems. And there's two elements to that. Yahia mentioned that I run a centre for doctoral training, which is an experimental PhD programme that's fundamentally cross-disciplinary, where we recruit artists, creative people, yes, computer scientists, management people, philosophers, psychologists to think about digital futures. And that's taught me so much about the world, and it's taught me so much about the way education should be in the modern age. But I'm not talking about that specifically tonight, although that's an underlying influence. What I'm talking about tonight is how informatics can help environmental science. You've already had some talks in the series, and perhaps some of you have been there, looking at some of the problems in environmental science today. What I'm talking about is the role of informatics in tackling some of these problems. So that's where I'm going to be heading over the next half hour or so. Before I do that, the underlying technology is cloud computing. And I have to hold my hands up here, because my own subject has an awful habit of mystifying things. And perhaps some of you are here to try and see cloud computing demystified. And I hope I can do that to a certain extent. A lot of it's jargon. If you strip away the jargon, it's actually much simpler than it seems. So one of my goals today is to try and give you a good intuitive feel for what cloud computing is all about. I used to say I worked in distributed systems, and people would look at me blankly. What's that? Now I say I work in cloud computing. Everybody knows what I'm talking about. You can even see cloud computing in Christmas adverts on television now. It's all around us. Maybe not so many people know what it means, but it's pervasive. It's all around us. It's becoming very important. It's becoming so important. Even this guy has got something to say about it. So I thought I would start, rather than Gordon Blair's view of cloud computing, let's hear what Stephen Fry has to say.
Now, as with water, electricity and gas, computing is also a utility. It is a resource to be switched on and off. Users consume and pay for as much as is needed when it is needed. This is the essence of cloud computing. Utility-based computing enables businesses to exactly align technology expenditure with requirements, bursting instantly from 1 to tens of thousands of users and back down again. Information technology departments can dynamically scale processing, memory and storage, only ever paying for the amount that is used. Before the revolution, in the dark ages of computing, companies bought technology based on what they guessed they might need in 3 years' time. If they bought too little, they ran the risk of having underperforming systems, meaning unhappy customers and possibly lower profits. So it was better to buy more, just in case. Today, any sized business can have access to the security, compliance, transparency, scalability and reliability of systems which until now have only been affordable to the largest companies on the planet.
planet. Edited that a bit tight. Thank you, Stephen. Have you got that? Perhaps a little bit too fast, so let's go through it a little bit slower and unpick some of the core ideas behind cloud computing. So what is cloud computing? Well, cloud computing came about really almost by accident. It came about because many large companies were starting to invest in large-scale computing facilities. The best example is Google, and these are pictures from some of Google's infrastructure. Google invested in technology because they have to support us doing lots of searches all the time. And we expect any search from all the knowledge of the world to come back in about 0.2 of a second. So when you think of the scale of the world's population, the number of Google searches that are done in any given second, they need a very large distributed infrastructure with something like 500,000 machines, which are constantly scouring the net, reading web pages, indexing the web, and allowing us to sit there and Google next holiday, where we want to go. Let's say Skye. It's a beautiful place to go. I'm sponsored by the Scottish Tourist Board tonight. That is a mammoth task, and we tend to take it for granted. It's a huge feat of engineering that you can search all this content and get an answer back straight away, all beautifully prioritized, so the most important searches are at the top. But what they finished up doing is building a massive infrastructure, which they actually don't use a lot of the time, as did Amazon, for example. Amazon supporting us doing our Christmas shopping online. Huge infrastructure behind the scene, a lot of which is not used for most of the time. So companies were setting up these huge data centers, which are underutilized and an asset. So what happened was that companies started to realize that perhaps we can sell some of the services on that infrastructure back to the general public. And that's got to the stage now where for companies like Google and Amazon, cloud computing is bigger business than their core business. Google is now a cloud computing company, not a search company. Amazon is now a cloud computing company, not an e-commerce service. So it's become huge for them. And what they're doing is they're actually moving applications and services from what would normally sit on your desktop at home with you, actually on your desktop. They're moving applications and services and even computing itself out there into the internet. To use a simple example, where's your data stored? If I asked you that question a couple of years ago, you'd probably say it's on that disk that's sitting on my desk at home. If I ask you now, where's your data stored? It's probably in Dropbox, which means it's stored out there somewhere. It might actually be on that machine there. You probably don't even know where it's stored. It's moved out there and it's into the internet. So the internet is not just a set of web pages now, it's actually services which are made available to you to supplement what you have at home as computers. So it's out there in the internet, which means that anything you put in the internet is available from anywhere. I came here relaxed tonight knowing that if my computer breaks, my PowerPoint slides are in Dropbox. So I just have to find somebody else with a computer and I can access them. I could access them from anywhere in the world and they're there, absolutely guaranteed to be there. They're shareable, they're out there, and they're open for other people to access, and we'll return to that in big time when we come to look at environmental science. Also, I don't own Dropbox. I don't own that storage. Dropbox are selling or renting a service back to me on a per usage basis. So it's a very different economic model of computing. We don't have to own resources. You're renting them for what you need. And if I need more, if I need to, for example, store the video of this talk later and I don't have enough disk storage, I can ask for more. and more, and grow or shrink, one of the key points that Stephen Fry was making in that short video clip. And this is a very flexible model of computing. It's one that's becoming very attractive. It's becoming very attractive for businesses. I'm not going to talk about that tonight. I'm going to talk more about how it can change science. But there's another talk as well on cloud computing, supporting businesses, supporting startups, supporting young companies that don't want to invest up front in a lot of computing resources. Two intuitive examples. I've already talked about Dropbox. I threw that in straight away because it's a very easy example to get. It's one we all use. If you're using Dropbox, you're actually storing your data in Amazon. Chances are it will be stored in Ireland somewhere, but you don't necessarily know that. So if you use Dropbox, it's stored out there as a service and accessible from anywhere, and you're constantly syncing your machine against that, or machines plural. Google Docs is another. In fact, the whole suite of Google applications, Google Calendars and so on, are another good use of where rather than having Microsoft Word on your machine, you've got Google Docs, so you can edit docs which are actually out there in the internet, which means if you're writing collaboratively with other people, or you've got your Christmas list that you want to share with your family members, you can have it in Google Docs and everybody can see it. Because it's out there, it's actually in Ireland somewhere, and they can all see it. And this has been a huge revolution in computer science. It's completely transformed the way things are going. Sometimes you hear hype around cloud computing, but the hype around cloud computing is very real. Yeah, it's been a major transformational force. Whether it's a force for good or not, we'll come back to, because I think that's a very important question. There are big concerns over cloud computing. I keep saying we'll come back to things. Somebody sit with a little checklist and make sure I do. I promise I will. So why would you do this? Well, I've tried to capture the kind of main reasons out there. One of the most important things is sharing. Things are out there that can be shared, they're open. And this is a big thing for science, to have data from science which is out there. One of the main motivations for what I'm talking about. You can also build on top of what's out there very rapidly. One of the most common things now is to take, somebody has been clever enough to develop a service like Google Maps. Well, one of my friends is very keen on cycling, and he lives in London, and it's very hard to cycle in London, and there's not much knowledge about good cycle routes which are safe. So what he did was he developed a service on top of Google Maps, which is actually really easy to do, which showed and allowed people to share cycle routes, safe cycle routes in London, and then a community built up around it, and people would put in their own cycle routes. Really simple to do if you know what you're doing around web services. So we'd call that a mashup culture, building on top of what's there. And you can have a whole ecosystem of people trying out new services and trying them out there and see what works. There's also no upfront investment. Again, Stephen Fry picked up on this. If you're a company, you don't have to invest in 1,000 computers for all your staff. You can start off very small and it can grow. Other people take responsibility for managing computers. If you've ever managed computers in your household, perhaps your family members have got computers and they break, and you have to make sure they're backed up. They get a virus, you have to make sure they're clean. It's an absolute nightmare. Why not allow somebody else to worry about that and just use it as a service? And this pushing of responsibility from you as a customer into the cloud, to the cloud provider, is so important. There's also the potential, and I stress the word potential here, that by having a small number of computers that are used heavily, you could make computing less energy intensive. By all us needing our own computers, you're generating a lot of energy, which is drastic in terms of CO2 emissions. If a set of providers have a smaller number and they're keeping them busy all the time, there is a potential for cloud computing to lead to major energy improvements. Now that's not the case, so I'll come back to that again. I'll say that. I'll come back to that at the end. So just going a little bit deeper, if you're still with me. Yeah, you do look an intelligent audience, so I think you've got it. Just going a little bit deeper, I'm not going to step through this diagram very much, but there's different levels here, and that's one important thing to get if you want to understand cloud computing. Cloud computing is not a thing, it's a family of things which are very different. And people use this terminology, infrastructure as a service, platform as a service, software as a service, for different levels of abstraction of things that are out there on the internet. The ones at the bottom are very primitive. And the best example of this is, I want my computer. I want to go to Amazon, please give me a computer, and they'll give you one back. Now what you don't get back is a physical box. Well, if you order through Amazon eCommerce site, you might get that. But if you go to Amazon Web Services, the cloud provider, and say, I want a computer, they'll give you a computer back, but it actually sits in their data centers in Dublin or in California. And what you get is access to that computer for as long as you need it. It's actually a virtual computer rather than a physical computer. And you get it. You can actually get these for free. So it's a remarkable resource out there. You get access to, you can run anything you want from your desktop. It looks like a real computer. It is a real computer, it's just not on your desktop. It's out there on the internet. And that's a computer, it's a low-level resource. And that's infrastructure as a service. I'm going to skip platform as a service because I don't want to give you too much information. But software as a service is more intuitive. Software as a service is any application that might be useful to you as a member of the public. Calendars, shared documents, YouTube, Facebook. All these applications are applications which are out there in the internet which you can access as arbitrary pieces of software. And by placing data, you're placing it out there in the greater internet, and it's accessible to all. That's very different from this level where you're getting a low-level physical machine. Here you're getting a service, an application level service. But it's all cloud computing. And sometimes people get really confused because they jump up between these levels and don't distinguish clearly enough. It's all cloud computing because it's all out there in the internet. But there's different members of this family. And if you've grasped that, you're really starting to understand what it's all about. Who owns the cloud? A very, very important question here, and one perhaps that deserves some debate. Partly, who do you trust? A lot of what I've talked about so far is public clouds. They're owned by companies. Google, Amazon, Microsoft, Yahoo. They're all trying to compete against each other to offer you cloud services. There's a question there, if I give my data and actually have my computers running and reliant on Amazon, can I trust them? Or actually, do I trust these cuddly people at Google more? Who do I trust with my data? And that's a very big question, given a lot of the debate recently over what, for example, the US government might allow access to in terms of privacy of data. Or do you trust your organisation more? I'm a member of Lancaster University. Do I trust Lancaster University more than I trust Yahoo or Google? Perhaps I do. So as well as commercial organisations offering cloud services, organisations can. Lancaster University offer cloud services for people that work in the university. They offer places to store data, to maintain its consistency. They offer email services. They offer a whole range of services. That's known as a private cloud because it's private to that organisation instead of being public to everyone to access, if you're willing to pay the companies, of course. This one's really interesting, but it's not yet taken off, but it's one I really want to take off. Let's suppose a community would get together. Now, let's suppose there's an area in Lancaster that thinks, between us we've actually got thousands of computers. Could we all support each other? Could we set up a cloud that makes use of all the computation and storage resources we have at our disposal? And actually form a community cloud that's not owned by any organisation, it's not owned by any big business, but actually offers us unlimited storage and processing capability just by clubbing together. And this has elements of what's known as peer-to-peer computing. And technologically, it's absolutely feasible. And I actually think it's a way that we really should be going. Yet to take off, but an area of huge promise, an area known as community clouds. If anybody's inspired after this to set one up in Lancaster, let's do it. So what's all this got to do with science? Actually, quite a lot. This slide, if anything, captures why I'm doing this. This is my motivation. It's maybe something about getting older. You want to do something for the world. You want to leave something, leave a footprint in the world. And over the years, I've become very, very conscious of the threat of climate change. Even more so with my exposure over the last decade to environmental scientists. I keep asking them, what's the good news? And I don't really hear it. I hear that the climate is under great threat. And what I hear is that there's actually no debate over that. The debate is in the press. The debate is not in the scientific community. It's pretty much factual that we're faced with major climate change. What do I want to do about that? I have a family. My family will have children. I want them to have a future. What can I do? Well, what I can do is think, my skill sets are in computing. I understand cloud computing. I understand other technologies. Can cloud computing actually not solve climate change, because that's a ridiculous statement, but can it contribute to our understanding of climate change and allow science to be transformed into a science that can respond? And I think the answer to that is partially yes. The core reason I say that is that environmental science is under pressure as well. Environmental scientists are being asked to answer big questions. When you meet environmental scientists, they're like any scientist that goes back to that silo mentality. You'll find people that can tell you everything you want to know about a metre of soil. In fact, not even that. They'll tell you about worms in a metre of soil, or they'll tell you about the chemical composition of the metre of soil, or they'll tell you about how one particular plant will grow in that metre of soil. But ask them to tell you about the properties of the soil as a whole, they won't be able to tell you. But then ask them, well, actually, climate change is happening in the Loon Valley. What implications does that have? What policies should we make? What policies should we set to manage and mitigate the threat of flooding? What farming should we now do to prevent, with all this increased flooding, to prevent pollutants running into the river? Big questions that span a range of different sciences and different perspectives, and they really struggle to answer that, and they know they're struggling to answer that. And in a nutshell, that's where cloud computing comes in. It's not often you turn to the Royal Society for revolution. Quite an august and conservative body. But they've published this booklet, which is one of my favourite inspirations now, calling for a radical restructuring of science to integrate across domains and increase transparency, to allow all the perspectives of science to work together. Understanding climate change is not a problem for someone that works in flooding, a hydrologist. It's not a problem for somebody that works in soils and carbon capture in soils. It's not a problem for somebody that works in diffuse pollution. It's a problem for all of these people working together and understanding how the different sciences come together and the interface between them. And that requires a way of bringing people together, bringing data sets together, bringing understanding together. So what we'd set up, I'll just click through these. Whoop, not that much. What we set up was an experimental system, which we're hopefully going to see in a few minutes, that set about putting the cloud at the heart of a new kind of science, using the power of cloud to pull data together. And also other assets together. It's not just data, it's things like models, which will tell you what's happening or what's likely to happen in the future. For example, is it likely to flood tomorrow, based on the rainfall we've had recently, and given the way the land lies around this part of the world, is it likely to flood? So it's bringing data and models and discussions and other tools into the cloud that allow all these different perspectives to be pulled together to allow an integrative kind of science. And what we did is we set up an experimental system, and then we had interfaces onto this data for many different people. That's the other challenge here. We're not just talking to scientists, we're talking to the water industry, trying to understand water quality and whether water is likely to be polluted, because they're fined at the moment if the rivers are polluted and it gets into the water supply. We're talking to government agencies, trying to make policy over climate change. We're talking to the general public, and the general public are talking to us. Because one of the most exciting things about these kind of developments is that it enables a new kind of science, which is citizen science. There's so many examples of enthusiastic citizens providing data, for example, in bee populations, what's happening to the bee population across the UK. There's so many people willing to put effort in and to become scientists themselves. There's even examples of members of the public gaining insights which have been valuable to the scientific community. So not just people that look at this, but provide data themselves. Citizen science, a really, really exciting area of development. And at the heart of this is cloud computing. So what we do in cloud computing for environmental science is that we just pull everything together. We set up portals that allow us to look at the UK, to look at the Lune Valley, to look at the Lake District and see all the data that exists around the environment. What's the history of flooding? When did it flood? If it flooded, are there then any effects in terms of pollution in the rivers? And are they correlated? And what were the farming practices that fed into that? And should we be moving towards more organic farming? Because actually the pollution is turning out to be a really major health problem. And all these interrelationships between different areas, which is the key to what we're trying to do, unpick interdependencies across different areas of science. And the cloud becomes an area for exploring data, for feeding data into models. It's a tool for what-if scenarios. More than that, much more than that, it's a tool for pulling people together. The most important thing when you put data into the cloud is that the people that provide that data come with it. The skill sets come with it, and you're channeling all the different sciences together to understand, to discuss, to collate, and to form a general consensus about what we should do about these problems. So the technology is this much. Pulling the people together to do this new kind of cross-disciplinary science is really what it's all about. The cloud is just an enabler. So what I'm going to do now, I haven't got very long, so I'll do this fairly quickly. I'm going to actually try it out with my glamorous assistant. So we're now going to actually see some examples of, this is the actual system. This is the portal. And what you can see here is you can explore different regions. At the moment it's either the UK, or we can think globally about climate change and run global models right across the world. We can look at different topics: flooding, pollution, hydrology, water, biodiversity and so on, climate change generally. We can look at different topics and so on. What we're going to look at is flooding, because it's something that affects us all. So we're going to zoom in a map of the UK. And being very democratic, we've managed to map out an area in each of Scotland, England and Wales, and provided assimilated data and models around each of them. But we're going to look at the Eden area in Cumbria. We're going to look at that area. And what we see here is a mapped area of the UK. And what we see are different environmental assets. These different markers here are data sets, some live, some recorded, some video imagery, and also the opportunity to run models. So what we're going to do initially, just as a first example, we're going to look at the one up here, if you here gets there, which shows some data that was recorded and extrapolated for an area around, I've forgotten, Dakerbeck in the Lake District. Sorry, Newton Rig, sorry. Yeah. So if we just scan over this is the kind of thing we did to try and make things accessible. So what this shows is turbidity in the river, pollution in the river, effectively. And what we have as well is lots of video data that captures what's happening in that river at the moment in time. So scientists can look at that, and if they see a particular peak in pollution, they can look at what was happening in the river at the same time and can actually dive deeper and see higher quality images to try and understand what's happening. So the idea is to have lots of these resources. So if you look at a geographic region, you see many resources around the environment. What we're going to do is actually do some modelling now. We're going to look at flooding in one particular area. I'm actually going to run some models. So we've actually got different models. Scientists love to develop models. Complex mathematical structures which predict the future. There's lots of them out there. What we've actually done is taken two of the classic models which exist in environmental science. You don't have to know anything about these. These are predictions of when flooding will happen. So in the future they can tell you the likelihood of flooding given the current environmental conditions. We're going to look at top model. Top model is a very famous one. And top model can be parameterized. Again, we don't have to look at the details. But it can be parameterized for different scenarios. So we can start to think, is it likely to flood in the future? But what happens if we're so desperate for food because of food shortages that we have to intensively farm that region? We have to develop more and more agriculture and really work the land. And the land dries out, becomes compacted. Or perhaps we're wise and we think, well, what if we actually plant trees? Because plant trees are really good at drawing up moisture from the soil and actually removing the likelihood of flooding if we're wise enough to plant trees. So what we're going to do, I'm going to get you here to run a series of simulations here, assuming current conditions and then with intensively farmed landscapes. And also with increased woodland. So you can see the different colours up in here. What's actually happening there is quite amazing. They're actually running these models in the internet. These models have just been shipped off to somewhere in Ireland. They're executing and the results are coming back here. So we're using virtual machines in Ireland to run these models. They're actually very fast, so you're able to see the output in real time. So we actually have the models, the results all overlaid here. And there's one area that's very interesting. Let me just explain what this plot's saying. This is the rainfall. And this is the actual risk of flooding. So obviously some rainfall will be absorbed in the ground, some of it will be absorbed by trees, some of it's got nowhere to go, so it will flood. So what we have here, whenever you get a peak above that line, you've got a liability to flood. So if we zoom in that area, what we can see are the different scenarios. And what we can see here is that if we intensively farm, we've got a major problem. We actually have flooding for each of the scenarios, but intensive farming is disastrous. So by intensively farming, we're greatly increasing the risk of flooding. The other scenarios help, maybe not as much as we would have thought. Actually, we can see here the woodland actually does avoid flooding altogether and actually managed to take away that peak. What we have in the grey line here, this is historic data, is what actually happened. So you can actually see the model's pretty accurate here because the current conditions in the grey line match very closely. So these models are pretty good. There's been a lot of advances recently in predicting flooding, and that model is really accurate. So then we ponder, planting trees shows a dramatic decrease in the likelihood of flooding. Intensive farming is disastrous. And we can play around with these scenarios. A scientist can come in and change the different scenarios. I think that's about all the time I've got for in terms of a demo. But Yahia will be here at the end and is happy to step people through other aspects of the cloud environment should you wish to see it. Next steps. Never stand still. And the next step we're hoping to look at, I think, is very exciting as well. What we're trying to do is to look at a new technology, which is the Internet of Things. And the Internet of Things is a technology where you instrument everything in the world. Some of this technology is frankly ridiculous. Your coffee cup becomes an element in the internet. Everything becomes an element in the internet. It's a technology seeking a use in some respects. But for the natural environment, this could be very, very important. So what we're doing to complement the cloud technology is to look at instrumenting the natural environment to collect as many data points as we possibly can. This is a proposal at the moment. We don't know if we'll be funded, but what we'll propose to do is to take an area in North Wales around the Conway area, which is an area of great interest because it's very compact. It's got mountains, it's got a river, it's got the sea, it's got farming, it's got shellfish industries, it's got tourism, it's got everything in a compact area. So what we're doing is we're setting up a large-scale sensing infrastructure where elements in the landscape could become elements in the internet. And that includes sheep, which is something my wife is very excited about, because we're part-time shepherds as well as computer scientists. So instrumenting sheep, finding out their movement patterns. Sheep can actually be you've got to be careful with sheep in terms of pollutants if they get too close to rivers or lakes. What are their movement patterns? What's happening in the soils? What's happening in the waterways? How's that influencing the shellfish industry, which is actually a major problem in Wales? What we're trying to do is to unpick what I think is probably my favourite word of the moment in this kind of new science, interconnectedness. Understanding the interconnectedness of everything in the natural environment. How these different parts of the ecosystem influence each other, soils and water and animals and humans. We might think this is divorced from us because we live in cities, but no, because it affects water quality, it affects health, it affects the availability of food, the interconnectedness of everything. So the next project we're looking at doing, and I stress that this is just a proposal, is to seek a knowledge of the interconnectedness of everything and how these different ecosystems interact in terms of having access to real-time data through one use of the Internet of Things that may be more meaningful than wiring up your coffee cup to the internet. So I'm almost finished. That's the team. That's Here looking very smart, and that's me looking not so smart. But just a few overall reflections. And behold, it was very good, or was it? I do not want to just come here and say cloud computing is great. I think you've got to balance that with a reflection of whether it's a positive thing. And there's certain things I really should point out. Let's do them in reverse order. Privacy. There's a big debate probably about 15 years ago in the press, for those of you that are young enough to remember it, over the concern over government databases, with the ability to link health records with financial records and so on. And that kind of blew up and then disappeared, and it kind of died away. What we must realise is that with the new cloud providers, the threat is much greater, maybe less explicit. But what we're actually doing now with the cloud, if you use Google Mail, if you use Google browsers, Google have that data. They know everything you've looked at on the internet. They can scan your email traffic. They can know an awful lot about you. Do we trust Google? There was a certain, and I'm not picking out Google, because for Google you can substitute it for any large organisation. There are major privacy concerns over cloud computing that are not really being debated. It's happening so fast, and we're moving so quickly towards cloud computing, we're not pausing to ask these very fundamental questions. We were asking the questions about government databases, but who do we trust? Do we trust our government? Yes or no? Do we trust Google? And what capabilities have they got at having this very, very rich data about us? Now, having said as well that my mission, I guess, if I could put it that strongly, is to try and use my skills to tackle climate change. What's happening with cloud computing? One fact that might shock you, it shocked me when I worked it out and I did some research on this. Cloud computing is going to surpass the airline industry in CO2 emissions. It's either happened now or will do in the next couple of years. Big data centres are going to produce more CO2 than flying. These big data centres are big. As I say, Google has something like 500,000 computers. Most of these companies are quite secretive about the size of their investment in this area, but you can extrapolate that the other providers have a similar amount. And just the amount of energy used to store what's become known as big data has just gone through the roof. So it's becoming as big a threat to the planet as flying. We're all very conscious about flying. I've made the decision not to fly next year. I haven't made a decision yet not to do Google search. And Google search, if you do 2 Google searches, it's equivalent to boiling a kettle. It doesn't come for free. The energy usage of these systems is huge and growing. So a few closing remarks, which sort of hopefully tie up a lot of what I'm saying. Disciplinary structures, which you could call silos. Other people would say it's a positive aspect of university. I would say it's disastrous, are a major barrier for many of the grand challenges of today. I'm motivated by looking at climate change. There are other grand challenges. For any grand challenge, by its very definition, it means people have to work together. And it's not just scientists, it's social scientists, psychologists. We have to move away from an education system that's so sold on the power of the single discipline. Academics should not be afraid to engage in real-world challenge. In fact, there's been such a profound change in universities, and it's one of the reasons I'm proud to be at Lancaster. I almost don't have to say this at Lancaster, because you'll have heard in the talks, our academics are addressing real-world challenges. They're not ivory tower academics by any means. They're getting out there and really trying to make a difference in the world, and they're passionate about that. Impact is not a dirty word and shouldn't be in academia. It should be what we're all about. Cloud computing can, and we've got enough evidence of this, it can facilitate a new kind of integrative and open science. This could be transformational. There's a lot more work to be done, and a lot of it's about changing people's habits and making scientists realise it's a new world and to embrace this new world and to move towards open data, for example, publishing their data sets. Open data is great. Open data is the way to go. This applies to scientific data, it applies to government data, it applies to all sorts of data sets. It's such a positive step forward. But big data is disastrous. When you look at what's happening in the world today, big data is probably the most commonly used word, and nobody's actually stopping to say, is this a good thing? Why do we have big data? Do we actually need more data? Economically, this might have an advantage in that it will allow Amazon to predict what we're going to buy our partner for Christmas before we even know. And they can have an advert up there because they can analyse all your patterns of expenditure and know you better than you know yourself. Is that actually a meaningful thing for society? Is it worth the CO2 emissions compared to the airline industry to be told what to buy our partner for Christmas? I think not. I think we've got to stand back and say that big data is bad, potentially very bad. And we should say, stop. We need less data. We need smart data. We need the right data. For example, data that helps us understand climate change, but not data that predicts our spending patterns before we know it ourselves. And perhaps a final statement. The world I work in now, the world of science, is very powerful. The world of computer science is very powerful. We're building systems now that have huge capabilities, positive and negative. And that's true of cloud computing. It's true of so much of what science has done across the last century. I think it's very important that scientists that develop innovation take a responsibility and harness this for the good. There may be, of course, debate over what good is, but I'd like to say that digital innovation and scientific innovation really has to be harnessed very carefully for what is meaningful and sustainable for society, so we can harness our innovation for the good of society and really have a debate over what that's all about. Thank you for your attention.
Thanks very much.